Good evening, Dr. Elaine. The following problem is number 24 on page 460 on angular momentum, and it's given a scenario. Well, this diagram will help. Where two masses, both of equal mass, are connected to a barbell and is spinning, and it's asking the following things in the problem below. So, the first one was asking was speed of the ball 1. They told us to treat the object as two separate balls, even though it's the same mass. The speed of the ball, so v equals r1 times angular velocity, where r is radius and w is angular velocity, and we just plug in the values that were given in the problem. Then the all transit ball 1, so which is p equals m times v1. That was the momentum of the ball. Then we get 4 kilograms times meter per second, and then the angular translational momentum is equal to r times p times sine of theta, where sine of theta is the angle between r and p. And we get 0, 0, negative 40 kilograms per meter per second. So I did the right hand rule here, so hold my left hand, and it was tilted like this. That's r. So, and you have to rotate to p, and it points inwards towards the desk. So that's why it's negative. Same thing, all transition for the ball too. Well, if they both have the same mass and they're both in the same direction, you know, we can just say or assume that they have the same values. But here's the calculation, and you do get the same value for the angular momentum for the second ball. Part D was the total transitional momentum, which is just the sum of the first two. We get negative 80. For the direction, I assume that since they're both negative, there's no way it's going to be positive or anything. Since we double check with the right hand rule, this does justify it. Then part E was the transitional energy of the ball, which is just kinetic energy equals 1/2 mass times v squared, and we get 10 for one ball, and 16. That's a 16. Yeah. For ball 1 and ball 2, once again, same values, so they should be the same. And the total was just the addition of these two, when you get 32 joules. So that was using it to where each ball had its own evaluation. Now we're doing it as the object is just treated as one barbell. So the momentum of inertia of ball 1, we're on h by the way. So momentum is I equals m times r squared, and we were given mass and the radius, so we get the value of 5 times 5 times 10 to the negative 3 kilograms per meter per second, meters per squared, sorry. The units here, it's kilograms, and then meters is squared, since radius is squared. So the units should be kilograms, meters squared. And then I for ball 2, that was for ball 1. I for ball 2, we get the same value, no surprise there. And then I have the rod. The rod is, in the problem it states that it's massless, so that's why it's 0. And you do have to calculate the momentum of the rod. And then the total momentum, the momentum inertia for the barbell was the I of the rod plus I of ball 1 plus I of ball 2, and we get the value of right there. Okay. Barbell spinning clockwise. Okay, this is where are we at? Right there. This was it was asking to find the angular velocity of the speed, and since for the direction, so the calculation was w equals 80 rad per second, and it's in the negative z direction. So once again, it was clockwise, and that justifies it. The rotation of the ball is equal to the transitional of the ball for A and B, so we get that. The rotation kinetic energy is equal to kinetic energy, and we get k rotation equals k rotation 1 plus 2, which is 32 joules, and they're both the same since they both have the same value, and regardless how you do it, they're all the same in momentum inertia and the angular velocity. So overall, the key important thing for this one, that was spinning in clockwise, that's what determined the direction. And that's it. Thank you.